Now we are going to be discussing thin-walled pressure vessels. When we call it a thin wall, we mean that the radius from the center of the pressure vessel is much larger than the thickness, specifically 10 times larger. The inner dimension of the pressure vessel is used for all calculations. Specifically, we're talking about the inner radius. In long pressure vessels, there are two different types of stresses. Circumferential stress, which is the internal pressure times the inner radius over the thickness of the wall, and we call this sigma 1, and this is the worst case scenario. There's also longitudinal stress, which is basically finding the stress in the end caps. This is called sigma 2. If you notice, it is the same equation but now divided by 2. Then, of course, there are spherical pressure vessels. They have the least amount of stress because they only have the longitudinal stress, or sigma 2. To help understand why these equations are like this, I drew part of a pressure vessel in SolidWorks, and I aimed it at making them easier to understand. If you want to use a more theory-based explanation as to why pressure vessels feel the stress, you may want to study your textbook, but I'll try to cover a very generalized and basic concept here in this video. First, when we look at a longitudinal pressure vessel, we notice there are two different geometries. One is the geometry of the end cap, which is spherical, and the other which is the geometry of the side walls. First, we'll look at the side walls. We can make a cut that is very small. Now let's imagine if that cut had pressure applied to it. As you notice, the amount of material that is resisting the pressure is quite small. Due to this, the stress that will be developed in this manner will be much larger. That is why the equation for this portion of the pressure vessel is PR over T, and not over 2T. Now if we look at a spherical end cap, we notice that there's a lot more material, but also there's a lot more of area that is being covered. But what we should notice that is important is that we have twice the amount of material holding it together, because you have both sides resisting, not just one side of the pressure vessel. That is key to understand why this equation becomes PR over 2T. Now let's do an example problem on the basic concepts. Here we have a pressure vessel, and we want to find the stress developed in the longitudinal and circumferential directions. First, we need to calculate our radius, and then we just use the equation for each. First for finding sigma 1, and then for finding sigma 2, which is half of sigma 1. As you can tell, this was pretty easy, but now we are going to do another example problem that is more difficult and might need some help seeing when you have your own homework problems to deal with. In this example problem, we are going to be looking at a pressure vessel that is being held together by bolts. We are going to look for the maximum internal pressure. We're going to assume that there are only two possible ways of failure, for simplification's sake. One of them is for the pressure being so high that it busts a hole in the wall. That is dealing with sigma 1, and that value is what we can learn was pretty easy to calculate. The other is if the bolts were to fail. If the bolts were to fail, then there would be a gap large enough for all the contained fluid to escape. Now if we want to do this, we will need to calculate each and then compare them. First, let's calculate the sigma 1 value, which is just PR over T. We of course will need to solve for the internal pressure, and we will call this the pressure that the wall can withstand. That gives us an internal pressure max of 416.67 psi. Now we're going to talk about the chance of the bolts failing on the pressure vessel. In order to calculate this properly, you will need to focus on some of the concepts that are important to understand. First, you'll want to cut along the bolts, then a section from the middle from one end to the other. Basically, you're going to make a cut that is a bolt spacing long. Next, we will look at the orientation. You'll notice how, if I put force on either side of the pipe, that it is because there are bolts on either side of the vessel holding it together. That force will be derived from the diameter of the bolt and the maximum stress that each bolt can handle. Then we will take into account the pressure that is pushing against the pressure vessel. I purposely put the pressure on the bottom face because that will help facilitate calculations. We can imagine the rectangular area being covered by the pressure while it is being distributed across it. Just to see the rectangular face that it will be covered, this is the correct orientation, the dimensions used to find the rectangular cross-section. Now we'll go ahead and start our calculations. Since we are going to have to compare the capacity of the bolts to the pressure inside the vessel, we can set these equations equal to each other. Then solving for the pressure, we can get an answer of 937.5 psi. Then the maximum pressure that this is going to be able to take is going to be the wall pressure, because if we can pass the value, it will burst. Then the maximum pressure that this pressure vessel can take is going to be our wall pressure, because if we pass this value, it will burst.